heat starts to actually do that. I think the hardest part is easily press when it goes to the stuff.
So chapter 10 is relatively short chapter, and it deals with reactions of alkynes. And so there are relatively few questions. Which of the following undergoes the reaction shown below? So that's first exercise. And you have unknown compound that reacts with sodium amide and isopropyl bromide to produce an alkyne. And there are 4 choices. And out of those 4 choices, you can see all of them are alkynes. That means it's conversion of one alkyne into another. And when you consider all of these 4 choices, actually you have already other answers here. Compound C is the correct one because the reagent is sodium amide, strong base. And strong base can react only with terminal alkyne because terminal alkyne has an acidic proton. That's the proton attached to sp hybridized carbon, and that one can be removed by a strong base. All of the remaining alkynes are internal alkynes, so they don't have proton attached to sp hybridized carbon. And so none of these protons that are present in other compounds, A, B, or D, are acidic. Only this is the acidic proton. And upon deprotonation, acidic proton, as shown here, is removed, and alkyne is converted to corresponding acetylide, which is good nucleophile. By now we have covered chapter 12 and SN2 reactions, and you know that this is an SN2 reaction. So strong nucleophile displaces bromine to give alkyne as a product. And here are 2 different formulas, 2 different representations of the alkyne. So that will be first question. Second, how would you prepare 1,2-dibromo, 2-chloropentane, starting with 1 pentyne and inorganic reagents? That's kind of common question in organic chemistry, organic synthesis question. And you're given a hint that more than 1 step may be necessary, which is also quite common, that in organic chemistry to prepare desired compound, we need more than 1 step. And so here is the answer. We start, when answering this question, always try to do it on pen and paper. Don't try to kind of imagine what would be correct answer, try to work it in your head. Use pen and paper. So if starting material is 1 pentyne, write that down so that you know what you're starting with. And you also may want to write down formula of the product. So that way you can kind of figure out the pathway. So first step is addition of hydrogen chloride, because you need to introduce chlorine in position 2. Addition of hydrogen chloride proceeds following Markovnikov rule through more stable carbocation. That means more substitute carbocation, which is on carbon 2. And that means chlorine adds to carbon 2. It's very important to specify that we are using only 1 equivalent of HCl. So addition of 1 equivalent of HCl will result in formation of 2-chloro-1-pentene. And then, of course, addition of bromine across double bond gives the desired product. On a test, you may be asked to provide reagents. So what are the reagents? And so on a test, you would simply type them up. So 1 HCl and 2 bromine. Since you're typing your answers and you're using Canvas, I don't expect you to use subscript. So this would be acceptable answer. 1 HCl, 2 Br2. But you have to clearly state 1 and 2. You cannot mix up these 2 together and just throw them in reaction mixture and expect to get the product. So you have to state first reaction and second reaction. By the way, if I asked, I will delete this answer, but let me just type up alternative answer. Let's say I asked how would you prepare 2-dichloro pentane. So 2,2-dichloro pentane, that means 2 chlorines on second carbon. So when you look at this second carbon, so chlorine, nothing here, just hydrogens. So 2-dichloro-pentane. Simply it would be addition of 2 molecules of HCl. So you would simply write 2HCl. So simply by writing HCl, I'm assuming that you are adding 1 equivalent. So if it's 2 equivalents, you would put 2HCl for 2 equivalents. So that's the question number 2. So before I move on to question number 3, let me check if there are any questions. Could the steps for number 2 be reversed? They could be reversed for number 2, but what I told you is better. It's better HCl and then Biart.
Professor?
Question number 3. What is the correct reagent for the reaction shown below? So in this case, we have reduction of an alkyne. We have somewhat complex alkyne, internal alkyne with 2 substituents, cyclopentyl group and ethyl group, and that's reduced to an alkene. And from the line formula, you can see that's trans. So what is the correct reagent for the reaction shown below? And actually, I can see right now that I have made a mistake. This was supposed to be cis, but I don't have now a program to fix that, so I will fix that. So this question was intended to ask you what is the correct reagent for reaction shown below, where the product is actually cis alkene, not trans. As written, actually correct answer would have been D. So correct reagent for this reaction would have been D, sodium in liquid ammonia. And actually this should be liquid ammonia. Okay, you guys are chatting too much, and that's distracting to me. So I have to ask you to please be quiet. Okay. So now let's assume that this is cis double bond, as it should be, and as I said, I will fix it. So first, hydrogen palladium on carbon. That's not correct answer. That would result in exhaustive alkylation to alkane. All the double and triple bonds would be reduced to alkane because carbon is only solid support for palladium. Carbon doesn't do anything. It allows carbon to spread over, it allows palladium to be spread over large area in thin layer so that we use very little expensive palladium. So that's not correct. And the same goes for B, silicon dioxide. Silicon dioxide is not correct. That's another support, alternative supports to carbon. It's also a reagent, a solid support that allows catalyst, palladium, to be spread over large area. So again, palladium is very expensive, so that we don't have to use a large amount of expensive palladium. This allows us to use very small amount of palladium spread over large area as efficient catalyst. But again, product would have been alkane. Correct answer is C. Hydrogen in the presence of palladium with pyridine. That's so-called Lindlar catalyst. Pyridine is catalytic poison. So it poisons palladium, makes it less efficient as a catalyst. And so now, as it's less efficient as a catalyst, it will only react with more reactive alkyne, triple bond, but it will not react with less reactive alkene, double bond. So it's only capable of reducing triple bond to a double bond, and it leaves double bond alone. So that one is correct. And since hydrogens are delivered from the same site, then product is cis. So as I intended this question, correct answer is C for cis product. Let's see. I will provide a little bit more right up here. And question number 4. What are the products of the reaction shown below? So here we have an alkyne, and reaction is, if you can recognize it, ozonization. Ozone in dichloromethane at low temperature, followed by aqueous workup. So ozonization results in cleavage of a triple bond. So triple bond is completely broken, it's cleaved, and in general, when ozonization is carried out on an alkyne, each carbon of the triple bond ends up as a carboxyl group. And when you look at these answers, this carbon on the left, carbon 2 of the triple bond, ended up as carboxyl group. But when there is a lone carbon, a single carbon, that means terminal alkyne, that single carbon of terminal alkyne is actually completely oxidized to carbon dioxide. So that's the only carbon of the triple bond that does not end up as carboxyl group. It ends up as carbon dioxide. So these are the two products of ozonization of the starting alkyne. So that completes a relatively short review of chapter 10. We'll be doing next much longer review of chapter 11. So first let me see if there are any questions. Okay, I don't see any questions. So let me stop.